Suppose we have a situation where there are some number of states and there's some probability of moving from one state to another at every step in time. This sort of situation is called a Markov process or a Markov chain. And we can draw a picture of a Markov process like this. So there's sort of one bubble for each state. So this graphic came from Wikipedia, so A and E don't really mean anything, but just to attach some meaning, let's say that maybe state A is being active and state E is being exhausted. Okay, and since at every step in time there's a probability of moving from one state to another, and that's what these arrows are showing us. So if you're active, the probability of becoming exhausted is 0.4, and if you're active, the probability of becoming active again, so staying active, is 0.6. And then if you're exhausted, the probability of staying exhausted is 0.3, and if you're exhausted, the probability of becoming active is 0.7. You can see that there's, for each state, each arrow has sort of an input end and an output end, and each pair of inputs and outputs has a number associated with it. So, we could have state A and state E. We could have these as inputs, and also A and E, we could have them as outputs. So if you're coming in at state A, going out at state A, that would be 0.6. And coming in at state A, going out at state E, that's 0.4. And then 0.7 and 0.3. So you can see that one way to describe a Markov process is actually with a matrix. Right? We have a square matrix. And the thing that makes this sort of the characteristic thing about this matrix that makes it make sense as a Markov process is that the sum of each column is 1. And that has to be the case because remember, what is down each column is the probability of different outcomes given that you started in the state for that column, so state A here. Well, if you start in state A, something is bound to happen, and so all of these probabilities need to add up to 1, right? Because the probability of something happening is a certainty, and that's a probability of 1. So each column needs to add up to 1 for a matrix to make sense as a Markov process. I guess also all the entries in this matrix have to be greater than or equal to 0 and less than or equal to 1. Because probabilities have to be between 0 and 1. So any Markov process like this we can turn into a matrix. This matrix is called a transition matrix. So that sort of depicts all of it. It's a nice way to package all of the information that's presented in this kind of diagram. All right, so a Markov matrix is just a matrix corresponding to a Markov process, right? Down each column. So if you sum down each column, you have to get 1. But remember, in the original setup, we sort of had some things that were in states, and the picture, the diagram, just told us how you move from state to state. So how can you describe the actual state that you're in? Well, we'll describe the state that we're in with the state vector. Okay, state vector just has an entry for each state. So for this kind of situation, we'd have an entry for state A and an entry for state E. And what the number of what this entry in a position means is essentially the population of that state. So one way to think about what a Markov chain is doing is you can imagine putting some number of tokens on each state, on each bubble, and then at each step in time, you move each token according to the probability. So you pick up a token, roll a die maybe to decide which of these two arrows you follow, and then you follow that arrow. So at every time step, you move every token according to the probabilities, and that sort of redistributes all of the tokens to the between the states again. So that's the idea, but what's the link between the transition matrix, Aij, and this state matrix, Xi, or which I guess we could just call X? Well, the way we have things set up, if we take our transition matrix, so remember our transition matrix, 0.6, 0.4, 0.7, 0.3, right? So we have our in states here and our out states here, right? These numbers are telling us the probability of getting certain out states going out, given that we're in a certain state going in. Well, if we only had one token, right? Only one individual, I guess, that was either active or exhausted. If we have one individual that's active, what we're saying really is that the probability of the person being active is 1, because they're definitely active, not at all exhausted. If we multiply this by this transition matrix, what we get is a new state, but it's a state that might have decimal entries, right? 0.6, 0.4. And there's two ways to interpret what this is telling us. The first way is we just have to imagine that instead of having individual tokens in our population, we actually have infinitely divisible things. So maybe instead of one person, this is like one cup of, I don't know, nanorobots. And so after we let time go forward, so we and see what all the probabilities do to transition all of these cupful of nanorobots into different states, 60% of the nanorobots are still active, and 40% of them are exhausted. The other way to interpret what these decimal values are telling us is that these numbers are all in the state vector. These are all probabilities. So if the probability of our individual being active is 1 at the beginning and exhausted probability 0, then after one time step, the probability of this person being active is 0.6, and the probability of them being exhausted is 0.4. So, you can think of this state vector either way, as telling you probabilities or telling you populations of each state. If they're populations, they can be anything that's positive, but if they're probabilities, then the entries in the state vector have to add up to 1. Something that's worth checking is if you start with a state vector whose entries add up to 1, and you multiply by a Markov matrix, then the resulting state vector also has entries that add up to 1. So that's a good little exercise. All right. So this is sort of the setup for a Markov process or a Markov chain. We have a transition matrix. We have a state vector. And there's actually a state vector for every step in time. And to get from one step in time to the next step in time, you just multiply by the transition matrix. All right. But that brings up an interesting question, which is there a steady state? So a steady state would be a state that doesn't change. Right, if we had such a state, I'll use the subscript S for steady state. Right, we want to know, is there a steady state? So is there a state so that when you multiply it by the matrix, by our transition matrix, you get exactly the same state back? Well, this is actually the equation for an eigenvector. Right? So if there is such a steady state, it's actually an eigenvector. And in fact, it's not just any eigenvector, it's an eigenvector for the eigenvalue 1. Okay, well, here's our transition matrix. Let's see if it has an eigenvalue 1, and if so, what the corresponding eigenvector is. So let's see. We're going to do our usual thing to compute eigenvectors. So determinant of lambda I minus A. So let's see. lambda minus 0.6 minus 0.7, 0.4, lambda minus 0.3. Sorry, this should be minus 0.4. So determinant of this. Okay, so lambda minus 0.6, lambda minus 0.3, minus 0.7 times 0.4. Okay, so this is lambda squared minus 0.9 lambda plus 0.18, I guess, minus, oh dear, 0.28. So it's possible I should have calculated these ahead of time so that you don't have to watch me struggle to do decimal arithmetic in my head. So this is going to be minus 0.1. Okay. All right, now we're looking for eigenvalues. So we have to check if we set this equal to 0, what do we get? And so I'm going to multiply. So now that we have this equation, I'm going to multiply this equation by 10, just so that I don't have to deal with the decimals like this. And now that I've done that, I see that this actually factors. So this is 10 lambda. Let's see, we're going to need that 10 to get a minus sign, so we need a minus over there and a plus 1 and a lambda. Right, so 10 lambda squared, there's minus 10 plus 1. Yes, okay. So over here we get minus 1 over 10. Okay, so we got this eigenvalue, but remember, we were looking for the eigenvalue 1. So the fact that minus 1 over 10 is an eigenvalue isn't super important for us. But look, here's another eigenvalue, the eigenvalue 1. All right, so we have, so now that we know that 1 is an eigenvalue, that means there will be a steady state. We just have to figure out what it is. So let's take our matrix and do A minus lambda I. And remember, the lambda we're talking about is 1. So this is going to be negative 0.4, 0.4, 0.7, and negative 0.7. You can see immediately that these rows are multiples of each other. So this is 0.4, 0.7, sorry, negative 0.7, 0, 0 when we row reduce. And this is going to have as so we're looking for a vector in the null space of this matrix, which is 7, 4. Right? Yes. Okay. So we found a steady state. In fact, any vector that is a multiple of this is also going to be a steady state. If we were looking for a steady state whose entries added up to 1, right? Because remember, one interpretation, one way of using a Markov process is if the state you're in is a probability. In that case, we need the sum of our states to add up to 1. And we can make that happen. We just need to take the steady state that we have and multiply it by an appropriate scalar. So the sum of these entries is 11, so we would just need to divide this whole thing by 11. So if we needed a steady state whose entries are probabilities, then it would be 7 over 11 and 4 over 11. Okay. So one interesting thing about Markov processes is, right, steady states are generally pretty interesting objects in these sort of processes, because even if you don't start at a steady state, over time you tend to head towards a steady state. That's actually something you could prove, but it's also sort of intuitively, I wouldn't say obvious, but plausible at least. So it kind of makes you wonder, if you have any Markov process, does it have a steady state? Well, let's check. We're going to describe this Markov process in terms of its transition matrix. And remember, the characteristic property of a Markov matrix, a matrix corresponding to a Markov process, is that if you sum down any column, you get 1, right? Okay, so we know that if there's a steady state, then 1 is an eigenvalue. So another way to ask the same question is, if we have a Markov matrix, is 1 an eigenvalue of this matrix? So to check if 1 is an eigenvalue for this matrix, right, well, I guess what we need to do is think about, like, the characteristic equation for this matrix. The thing about this matrix is we just don't know very much about it, right? We're looking for a solution to this equation, but we don't, right? In this matrix product, right, to calculate this matrix product, the vector v sort of gets tipped over on its side, and you sort of swipe downwards, doing products as you go. So, right, the vector v is doing linear combinations of the columns, and so the numbers that are getting all scrambled together when we do this product are the numbers across a row. And we don't know anything about what is happening across the rows of A. So what we know about is the columns. So maybe we should try to, instead of thinking about A, think about its transpose. Because the transpose of A, so if B is the transpose of A, then, right, Bij is equal to Aj, and then saying that Aij, when I goes from 1 to n, sums up to 1, right, that's the same as saying that that's the same as saying B, so sum from I equals 1 to n of Bji is equal to 1. And this is a sum across a row, right? So maybe we could interpret this as a matrix product, and that would let us use this fact about the sums of these entries being 1. So let's think about the transpose instead of the original matrix. But we're going to have to link this back to the original matrix somehow. So what is the relationship between the eigenvalues of a matrix and its transpose? Well, right, here's the characteristic polynomial for A. Maybe I should put x here instead of a lambda for now. Here's the characteristic polynomial for the matrix A. How's this related to the characteristic polynomial of its transpose? Well, we know that the determinant of a matrix is equal to the determinant of its transpose, like this, but also the transpose of a difference is just the transpose of the individual matrices, like this, but also x times the identity matrix, that's diagonal. And when you take the transpose of a diagonal matrix, you get exactly the same matrix back. Okay, so we get this. But look, this is the characteristic polynomial for the transpose. Right? In other words, the characteristic polynomial of B. So any root or any zero of the characteristic polynomial for A will also be a characteristic polynomial for B. So this means that A and B, and remember B is really A transpose, have the same eigenvalues. Okay, so if we can show that 1 is an eigenvalue for B, then we know it's an eigenvalue for A. Okay, but what do we know about B? Well, we know this about B. This is saying that rows sum to 1, rows in B. Okay, but we can add up a row just by multiplying by the vector that's nothing but 1s. Right? If you multiply a matrix by a vector that's nothing but 1s, that has exactly the effect of adding up all of the entries in each row. So this now is the vector so I goes from 1 to n of B I guess I need a j here. Bij, but right, this is the same as the sum from j equals 1 to n of AJI, but that's exactly what we said was equal to 1. So each one of these, each one of the entries in this matrix product is just equal to 1, 1, 1, 1, 1. But that's what we started with, right? So this shows that B does have, so B has lambda equals 1 as an eigenvalue. And so A has lambda equals 1 as an eigenvalue as well. Right, so this doesn't actually tell us what the eigenvector for A is corresponding to this eigenvalue. So this doesn't really give us a shortcut to finding a steady state, but it does guarantee that there is a steady state for any Markov matrix. So, you know, when we calculated a steady state before, the first thing we did was we checked that 1 was an eigenvalue for our matrix. It turns out we didn't need to do that. As soon as you write down a Markov matrix, it's guaranteed to have 1 as an eigenvalue. So you can proceed directly to finding a steady state by finding an eigenvector corresponding to the eigenvalue 1.